Thank you for the introduction. Thanks for the invitation to come and speak to you tonight. You will have already have noticed that there's a few pictures of mountains to start with in here, and there's frivolous reasons for that. Do you want to turn the lights down a little bit? Do you want to turn the lights down, Daisy, a little bit, just to sort of. I start with mountains partly because people are more interested in looking at mountains than looking at me. So I start with that. Partly because in some ways I chose architecture to study because it was such a long course that it gave me many years of long summer holidays to go off climbing mountains. But slightly more seriously, it was through travelling, I think, to mountains, and as you heard in the introduction, I was involved in the first Irish expedition to Everest 25 years ago this year, and which also we also made the first British ascent of the North Ridge, which for any Everest researchers was the route that Mallory and Irvine disappeared on in 1924. And that's the famous second step on the North Ridge where Mallory was last seen in 1924. But I suppose the sort of serious bit of this is it was through travelling to go and climb mountains in various places around the world that I started getting interested in conservation and architecture and heritage and the built environment generally. So there is a connection between that, but there's an even more important connection between this. And if you go right the way back in terms of when people started, I suppose, seriously studying in scientific terms, geology and the relationship between geology and the built environment. William Gray, who was president of the Royal Institute of Architects of Ireland at the time, back in 1878, there's a close connection between geology and architecture. And his basic principle is that an understanding of the natural world and of geology is important for an architect because you're understanding the basic material that you're working with. Because still today, one of the most basic materials we work with obviously is stone. And even if it's not natural stone in its form, it's a product which comes from stone or clay or sand. So to understand the natural world he said back then, is fairly fundamental for an architect working with the materials that come from the natural world. And it's something that's largely been lost, I would say, in architectural training. We sort of treat these things as products that come off the shelf, as opposed to natural living materials which respond to the environment and they're a product of the environment and how they were made in the first place. So understanding stone, and I'm going to be mostly talking about stone tonight, understanding stone is, I think, important as an architect, but even more important as a conservation architect because you're quite often restoring and conserving stone, which has been exposed to that environment again in a different way for 100, 200 or more years or so. I started getting involved in this, and this is a sort of the core theme of a lot of what we've been talking about here. On the left is Professor Bernie Smith. Some of you, I think, will know him. Bernie tragically died a few years ago, far too young. But Bernie, who I think was a tropical geomorphologist, I think was his actual subject, but not that there's much tropical geomorphology in Belfast, but he became, and I think it's reasonable to say, one of the sort of leading European lights in terms of understanding stone weathering, the weathering of natural stone, in particular sandstones in that. And part of his legacy has been taken on by the lady in the blue at the front, Dr. Patricia Wark, still in the Queen's University as well, who studied under Bernie and still runs that department. And then the other lady there is Joanne Curran, which was mentioned in there, one of Bernie's PhD students, a geologist, who came to us as through the Knowledge Transfer Partnership probably 15 years ago now, and we couldn't get rid of her, and she stayed, and she's still working, even though she's a geologist, is working on building sites, working with stone restoration ever since, and has been involved in a lot of the projects that I'm going to be talking about. Another crucial person in the middle comes from a completely different background. He's actually a joiner to start with. His name's John Savage. He started as a joiner, didn't go to university or anything, went straight from school onto the trades, became a joiner, very smart guy, became a clerk of works, got into stonework restoration. Again, we came across him on a building site and employed him. And he's the practical side of what I'm going to be talking about, because largely what I'm putting you tonight is this balance between the links between academia and research and actual construction practice that happens on site. And my experience, and still there's too much of a gulf between those. There's lots of good work goes on in universities, which we never know about working on building sites, and therefore we can't learn and we don't put into practice. But there's also things that happen on building sites and practical knowledge which would be useful to people in universities to understand the practical limitations of things, what makes a technique possible on a building site as opposed to something that can only be done in a lab. So what we've been trying to do for the last 15 or 20 years now is bring all that together, is to bring together the research with the practical work on building sites. And that's where I see my role. I'm sort of the master of none in all of this, but I try and connect the bits together. And the first project we worked on was this church, and this is 15, 20 years or so ago now. So a local sandstone in Northern Ireland, Scrabo sandstone, picked because it was really easy to work, and of course it was also really easy to fall apart. And in particular, it was incredibly susceptible to erosion from salts and pollutant damage. There are what's called spectides in it, which are clays buried within the stone. Those stones, when they get subject to water penetrating deep into the stone, start to swell, and it's the swelling of that stone effectively blew the stone apart. And so we have a huge legacy of these buildings in Northern Ireland, so it was very popular quarries, and they're all coming up now 100, 120, 150 years old. They're all starting to fall apart. And understanding why they were falling apart and what we could do to stop them falling apart was a crucial part of exercise. So this is one of Bernie Smith's projects. And we restored this church from the state on the left to the state on the right about, let's say, 15 years ago now, and it has stayed restored, if you like. It hasn't disintegrated further. And that was a combination of, in that case, of some repair, some replacement of the stone, but a lot of just simply removing the loose material, the application of a deep penetrating consolidant, and then a breathable water repellent on the surface. But understanding the processes that were going to happen to the stone with the application of those materials was crucial to making work. So we did tests. We tested this for over a year on real life tests on the building, and monitored it and studied it before we started working on the full building itself in the very particular circumstances. At the same time, Bernie had set up in different parts of Belfast stone weathering trials, different sorts of stone. But even though now we're not in Victorian heavy pollution days, there were still two things happening to that stone, to new samples of stone within 20 months. And say this is now, sort of 17 years ago. Firstly, in terms of biological sort of colonization of that, but also fly ash particles starting to grow on the stone. So even though, if you like, we've got rid of the Victorian pollution, there is still a lot of pollution in our air, which was affecting new stone within a relatively short period of time. And that's been happening. Belfast was a typical Victorian city, lots of heavy industry, lots of pollution, lots of coal fires, and the buildings suffered from that. And this is one of our best known memorial clocks, the Albert Memorial Clock. Black and white picture, obviously, as not long after it was built. The photograph inserted beside it, if you start to look at the loss of detail on that, if you look at the two tops of it, you can see on the right you had lots of extra sort of gables and carved stone. All that had gone by the 1980s because it had eroded away, was taken off, disintegrated, crumbled away, attacked from the pollution in the city. And even poor old Albert had lost the, if you look closely at, let's see if I can, nope. Here you can see he had a lovely little canopy to protect him from the rain. He'd lost it because it had fallen apart. It had disintegrated under the heavy pollution of the stone. And that was the state of the clock tower when we started work on it in around about 2000 or so. A lot of it's still that same Scrabo sandstone eroded away really, really badly. So we gave Albert a bit of protection just to keep him safe while we were working around him. Albert is Portland limestone actually, and that Portland limestone by comparison kept its carved detail and kept the sharpness very well. But we had to put back a lot of the detail on that which is gone. So nearly all the carved stone that you can see here going back is new stone going back in, replicating the original stone within that, because that detail had been lost. But when it came to the shaft of the stone, the main shaft of the stone, that's all the original stone within the building. And again, that was cleaned, repaired, and treated, and was fine once you went back beyond a certain surface within that. And again, that was subject to testing and trials for over a year before we actually started work within that. And Albert got us his hood back as well to keep him dry. It's not just sandstone, but limestone, and this is Portland limestone. This is Belfast City Hall, built and finished in 1906. But the picture on the left was taken in 1912. It was Edward Carson's funeral, and you can see how dirty the building is. You imagine that's meant to be a bright white building, only built 6 years, and yet within 6 years it had gone black as a result of the heavy industrial pollution. Cleaned in the 1980s. And has stayed largely clean since then. And of course, limestone, different things happen to limestone in that, and where it's washed by rain, it tends to stay clean. And the rain-washed areas, you get a dissolution, so the surface gets pitting and worn, but it tends to stay clean. But you get these calcium sulfate or gypsum crystals growing on the sheltered areas where it's not being rain-washed off, and this sort of typical blackness is gypsum within that. And Belfast is not unique by any means, but it does have some local characteristics, and there's other cities around Britain and Ireland that have the same, but we have obviously heavy industrial pollution from the mid-19th century onwards. It's on the coast, so you get marine salts coming in as well. And then because it's also in a dip between two groups of hills, in winter in particular, you get sort of anticyclonic high pressure systems just sitting with the air, sitting still in it and not moving at all. And the combination of those is fairly extreme weathering of the stone within that. And I'll not pretend to understand the science between all of this, but this is broadly speaking what's happening to the stone. So effectively, it's sulfur dioxide, which is in the pollution. It reacts with the calcium. The calcium can either be in the stone or in the mortar as well, forming calcium sulfate, and that's that black crystals that you see on the surface of the stone. And you get crystallization of that, then starts to cause damage of that, and eventually that breaks away, that surface breaks away from the front of it, leaving a depleted area behind, and then you get fairly catastrophic weathering of that depleted area, and it sets up this cycle of damage. And it doesn't happen to all stones, but you typically get some stones which are just weathered away and keep weathering away and keep weathering and keep weathering, whereas other stones around it can be fine around that particular thing. So it can tend to have this sort of catastrophic retreat. And all this happens in slightly different, well, very different ways in different areas. So in rural areas, with that we mean a clean environment where you don't get the same atmospheric pollution, it tends to be just a gradual weathering of the stone, erosion of the stone, and that's sort of a gradual sort of eating away of the surface, but not the sort of catastrophic. The urban polluted area, that's where you start to get the black crust, the black crystals, the gypsum forming on it. Bottom left is salt weathering. You can see the whiteness of the salt starting to come out. That's quite often associated with groundwater, water coming up, or marine environments where you're getting salt-laden air hitting the stone and you get the salts coming through. But nearly one of the most typical types of damage that we deal with is bottom right-hand side, and that's where for many years, certainly from 60s, 70s, 80s, even quite recently, people have been repointing buildings in hard cement-based mortars. mainly because they thought they were doing a good thing. It wasn't as if people were deliberately setting out to damage buildings, but it was seen as a way of protecting the buildings, to repoint them in its hard mortar. Quite often in a sort of ribbon, what we call ribbon pointing, so a sort of thick layer of mortar behind it. And there are buildings all around the country which have been repointed like this. The softer the stone that they're repointing, the worse the damage is, but the damage is pretty catastrophic, really, because what happens is that in the moisture within the stone and within the walls, and I'm going to go and talk a bit more about that in a moment, the moisture quite often comes out through the joints rather than through the stone itself. If it can't get out through the joints because you've got a hard cement mortar on it, more of it comes out through the stone, and therefore you get more of that breakdown of the surface of the stone as you get movement of water through that. And up and down the country, you will find walls like that which have been damaged by good intent, if you like, by people thinking they were doing the right thing, but in fact making it worse. And it still happens today, despite all the information and knowledge about it. You still see walls being repointed in hard cement mortars. There's another typical sort of weathering that happens, and that's in particular with these iron-rich sandstones. Giffnock is a Scottish stone, very heavily used throughout Scotland, but also a lot of it imported into Ireland and used there as well. And under acidic conditions, which of course again is polluted environments, the iron is mobilised to the surface. The iron comes to the surface, and as it's doing that, again, it tends to what's called case harden this surface. It's iron oxide in the outer layer. It's also characterised by staining of the stone, this sort of orangey red staining of it, and then you get this weakened layer just below the surface as well. In the thin section view below, you can sort of see what's happening to the crystals in the stone. And that again is very typical of the sandstone weathering in polluted environments. And this is, I suppose, an extreme example of it. The building we restored again about 15 years ago now. You can see that complete breakdown of the surface of the stone. And there are choices in this case where we either replaced a large majority of the stone, or in fact, what we did was actually redress the original stone back beyond that depleted layer. So we, if you like, took a shaving off the face of the stone. We had to replace a lot of the carved elements, but the main bulk of the stone is still there. You'd never describe that as really good conservation practice, but when you get extreme decay like that, you're really left with a choice of either replacing a lot of the stone or doing this redressing the stone back, building back in use again as a school library, in fact, and keeps the water out as well. And I suppose out of those are all early projects, but every one of them had an input from Bernie and his team into making decisions about what to do in each case. And at that stage, we were focused very much on the weathering of the stone and how the stone performed in the environment. And out of that came this project, which is the Northern Ireland Stone Database, which was our first KTP, and that between Queen's University and ourselves. And really the purpose of that was to get information out to the public about, and out to the industry about what we were actually dealing with. So this is still now, 15 years later, a live database. On it there's details of every stone building in Northern Ireland, what the stone is, how that stone performs. We also looked at all the quarries where that stone came from, both local quarries and imported stone as well. We linked it, it's all linked together by stone type, by geographical area, by the architect and that. And the purpose of this database was really so that people understood what they were dealing with when they came to it. So if you started to work on a building, you had a source of information to know what the stone was, how the stone weathered, where you could get replacement stones, what were the suitable replacement stones when you couldn't get the original. And that's been running now for the last, say, 15 years or so. And tied into that was the book that Joseph mentioned at the start, which is this one, which is intended really as a field guide for people working on stone buildings. Again, the purpose of this is really just to, it's recognition of this, of that a lot of people, and architects, surveyors, builders, they were described as prostitutes quite often, but we get hired for a job, and you go along, you do this job, and you're quite often under pressure from time. You're quite often don't know much about the background. You don't know much about the 100 years of history of that building that's gone before, and what people have done to it before, and what people, how people have used it. And you don't know much about how that stone has performed over the years, or what it's been treated with, or whatever. So the purpose of it is to try and get the purpose of this database and the book was to try and get information out to people about how do you go about surveying a stone building, how you go about looking at it, how you go about researching, where do you find information on the stone, how does that stone perform, what happens if you treat it with this or treat it with that, what's a suitable replacement stone. All that information is there. It's locked up in research papers and journals and databases. Getting it out to the industry is really difficult to do, making it accessible. So that's what the Stone Database Project was about, and what this book was about as well. And tied into that, this was another sort of side project, which was really back to this idea of linking geology with architecture. And this was a poster done for schools and universities at the time. And this was this idea that if you look around the historic fabric, it is a representation by and large of the geology underneath you. Not always the case, of course. People who had enough money imported stones from all over the place. But most cases, the underlying geology is reflected in the architecture, and that link is so often lost as well. So part of this was encouraging quarries to reopen, stone to be used, and I'll talk a little bit about that later on. But as I say, in the first number of years, we were concentrating really on this weathering process and the breaking down of the surface of the stone and what's happening and how to repair that. But as we went on, it became clear to us, and probably should have picked it up much earlier, that really water movement through the stone is actually the crucial thing in all of this. And understanding how water moves through a building's fabric is actually crucial to understand how that building is going to weather, and also what you do with it to repair it as well. So for the last 10 years or so more, we've been focusing more on this idea of water movement. And part of that is because that's why buildings go wrong, they leak. And most of the things that people complain about are the fact that water gets in to your building. So 50% of all defect types in buildings are to do with water getting in. So that's the sort of background of why water movement is important. But it's also, I suppose, been doubly important now because climate change is happening. It's real. We can see it. And one of the effects of that is greater intensity of rainfall events, tied in quite often with greater wind speeds as well. When we look at the weather data for Northern Ireland in particular, the actual total amount of rain falling isn't necessarily changing that much at the moment, but the intensity at which it hits buildings is increasing, and that has and is having dramatic effects on buildings. Buildings which have never leaked before, historic buildings, are now leaking. Water is getting through, and new buildings are suffering from that as well. So we've been involved again for the last 10 years or so in more and more projects to do with trying to understand that process of water getting through that, and that's what Scott's working on at the moment, is one part of that. But leading up to that, I suppose, so there's pretty obvious things about water, and as a country, we're incredibly bad at maintaining our buildings. Is probably the single most thing we could do to stop water getting in is proper maintenance of buildings, cleaning gutters, repairing eaves details and things like that. But where water is concentrated, and these are extreme examples, obviously gutters overflowing, but even just in areas where water slows down on a building, as it comes down the vertical slope and it goes on to a slope, and there's many architectural details where that happens, you can see what's happening. The water is slowing down, the water is staying on the building, and it's getting colonized in this case by algae. In some cases this is just aesthetic and doesn't really do much damage, but in other cases obviously vegetation growth can lead to it, and it's a sign that stone is staying wet, and as staying wet, there's more likelihood of the water getting in the buildings. So the sort of primary focus really in any work to building is actually getting the water off it in the first place. When we're replacing gutters now in buildings and repairing gutters, we're making them bigger than they used to be because gutter sizes need to increase because of the intensity of rain coming about. And I would say at the moment the gutter sizing tables for buildings are out of date because they're not really based on weather data or accurate weather data about rainfall. Making them accessible, so getting rid of bends like that, making them accessible so that you can clean them out, that they stay cleaned, putting in overflows to make sure you get a warning of blockages where they occur, and detailing the roof so that you don't get concentrations of water running off in places. I suppose this is really, put this in an example. This was actually a building that had been chemically cleaned and was pristine clean. And within a year, that had happened to it. So the owners weren't too pleased. It wasn't one that we cleaned, I'm glad to say. But this was because it was chemically cleaned, it hadn't been properly neutralized after cleaning. There were nitrates left and fertilizer effectively left on the building. Along came the water, all this detail, and it grew a little green skin all over it. And that was about a year that took after it was pristine cleaned. So water has an effect, but probably more seriously, water can have a devastating effect on the internal fabric of the building as well. This is another building which had been closed up for some years, and through a combination of a really complex roof, gutters being designed by the original architect not to be visible in lots of cases, so really contorted ways of getting water off a roof, which then blocked up because either the architect or the client didn't want to see the rainwater goods in places. Combined with lack of maintenance, the building was closed up, nobody looking at it, and pretty much the whole of the historic interior had to be ripped out in the end through rampant dry rot taking hold within the building. Dry rot obviously happens when you get combination of moisture, lack of air movement, and the food source, which is the timber, obviously. And it can be utterly devastating for a building. In this case, this was a full historic interior, which within 3 years of the building being closed up was lost completely through water. And that started from water getting in from leaky gutters, travelled through the building, combination of maintenance and nobody looking after it, and the whole of the interior lost within the building in a rapidly short period of time. So keeping water out is pretty important. So every time we're working on a building now in terms of re-roofing it and that, we're increasing the size of gutters, we're increasing the size of the downpipes, we're trying to get rid of bottlenecks, and we're also using more and more putting flashing details like this LED flashing in the bottom right to get the flow of water off the building. So designing out ledges and things. And some of this you can argue about architecturally because you're quite often changing the aesthetic of the building. But what we're trying to do is get the water off the building as efficiently as possible. So LED flashings on gullies, LED flashings on parapets, over cornices to get the water off the building. And the reason we do that is because we're finding that with that intensity, and particular intensity of wind-driven rain, we're finding that water is penetrating through even historic stonework, which hasn't leaked before, but quite often when you start going into it, you find it's always leaked anyway, or there's always been a bit of water, but you're getting more and more water getting through. And sometimes repointing of the building, which is nearly one of the first things you do, because you go along to the building and the mortar's crumbly and it's good, so repointing is one of the, if you like, standard things you do. Sometimes repointing the building can actually make it worse. Because what you're doing is that water always gets in. You have to assume that in any masonry wall, water is going to get in somehow. And it's partly because buildings move. You're always getting thermal movements. You get shrinkage cracks around mortar joints. So mortar may be filled when you put it in, but it'll shrink back very slightly. Buildings move. The smallest of hairline cracks, wind-driven rain will get into it. So you have to assume water is going to get in. So if the water can get in and you've repointed it, especially if you've repointed in too hard a mortar, you'll find that the water, you're actually encouraging the water to go into the wall and through the wall rather than back out through the surface again. So sometimes repointing, that's not saying you don't repoint, because quite often you have to, but sometimes driving the rain, you can be driving the rainwater in further through the wall. And the picture on the right is a rubble stone wall through, and all those damp patches are rainwater driving through. Sometimes you find that people, this could have been, I think this was a rendered building. It's rendered on the outside, and for aesthetic reasons, people take the render off and say, well, look at that lovely stonework. And then the water starts coming through, and you realize why it was rendered in the first place. We use a lot of breathable water repellents these days, and they are part of the solution quite often. But again, they're not a magic bullet by any means at all, we found. And that's because they can work on soft stones and they can improve the breathability. They can get water off the building, let water roll off the building. Firstly, they don't last forever. They need to be retreated. But secondly, they don't bridge cracks. They don't bridge those hairline cracks that we're talking about. So again, it can be part of a solution, but it's not the answer in many cases at all, because water still gets in to the building as well. Again, quite a few years ago now, with Queen's, with Bernie, Queen's, we were involved in this project, which was we built some walls in the wettest part of Northern Ireland. You got an average rainfall of about 1.5 meters, so that gives you an idea of how wet it is out here. And what we were doing here was we were taking new stone walls, embedding moisture sensors within that at different depths, and then setting it up with a weather station to see what happened. Now, what we're expecting to happen, and what, if you like, conventionally happens, is that sandstone particular, gets wet to a certain depth, and then when the rain stops, dries out again and comes back to the surface. And that's, if you like, the sort of conventional pattern, that's sort of the understanding. So we set up this, and it ran for, 2010, ran over the winter, 2010. And we were measuring the moisture content at different depths within the stone. And this is what happened, if I can briefly explain that. So you've got 3 depths. The sensors were at 5 centimeters back, so 50 mil back, 150 mil back, and 250 mil back from the face of it. And at the start, in October, you can see that we were getting that sort of wetting, drying action. It was getting wet, and then it was drying out, and it was getting wet and drying out. But that's the near surface bit. That's from 5 centimeters back. And what we were finding was that after a while, the intensity of the water was so much that it actually got up to full 100% moisture and stayed there. In other words, it stopped drying out very quickly, really. And if you think about that, 250 centimeters back, so that's that much back from the surface. In most stone walls we're dealing with, the facing stone will not be any deeper than that. Quite often, the typical stone wall, if you like, you've got a facing stone, 200 or 300 mil. You've then quite often got a rubble core or a gap, and then you've got another stone brick lining or something on the inside. So what we were finding in this, admittedly it was west of Ireland and it was raining a lot and we're getting strong winds. But what we were finding was we were getting full depth penetration of the wall, and it was staying wet. It wasn't drying out at all. And interesting enough is that as it got deeper, the wetting front started moving faster through the stone as well. So this was a sort of a bit of a shock to us, I suppose, in terms of understanding that, because I say all the work about repointing is really all about protecting the surface, letting it get a bit wet and assuming it dries out and moves like that. But in fact, in very wet areas in this intensity of rain, we're finding that the walls are getting fully saturated, and once they get a certain distance, then it's relatively easy for that water to start tracking inwards and to go through the core of the wall and in. And that's, I guess, is what we're seeing in practice, but this was the first time that we were starting to see it in reality. Particular on, so it's wind-driven rain is the particular one. So you get in Northern Ireland, and quite often most parts of Britain, southwesterlies is the prevailing strong winds bringing the rain with it. And so in sheltered northeast areas, you were getting this rainwater going in and evaporating back out again. But on the exposed areas, we're finding that although that's happening near the surface, the water is penetrating through and traveling full depth within the stone. And that, I suppose, is we're seeing more and more now, and it is partly to do with climate change and intensity of rain and wind-driven rain in particular, but moisture penetration is extending much deeper into walls than traditionally would have been thought, and traditionally we would have seen about that. And so you're getting this, I suppose, this change of thinking between, it's not this surface, it's not a surface phenomena, it's a full depth wall phenomena in terms of what's happening to this water, and we need to start thinking about how the water is then moving in the depths of the wall. This is not our project, but I put it in because it is relevant as well, and there's lots of people looking at this. So English Heritage ran, and there's still some outcomes of this coming out in terms of further research coming out. This is a few years ago now, what they call the Damp Towers Project, because they were also experiencing, I think this was sort of in the southwest area, they were looking at Devon, yeah, it was that particular one, but it was the southwest again, westerlies, and they this experiment, and the questions they were trying to understand was, how does the driving rain enter the masonry? How does it move within the masonry? And they were trying then different treatments and repairs for that. And this was a very interesting project, and a lot of learning came out of it. But as always, when you do these things, it asks more questions and sets off new trains of research. As well as looking at real buildings, they also set up lab experiments looking at these. At moisture movement through sort of test walls, if you like. One of the things coming about that, out of this, which I suppose we hadn't really thought of before, but it makes perfect sense when you think about it, is that at the top of the vertical joints, or we call the perpend joints, so at the top of these joints here, and it's even more pronounced on tighter joints and brickwork joints and as well, is that because it's very difficult to pack those tight, so the mortar on the top of those joints tends to be looser and not have the same pressure on it as it does in the horizontal joints where you've got the pressure of the next course. So quite often you've got weak or more porous spots at the top of every one of those joints, and they found that when they linked it up to experiments that the wall may look homogeneous, but the rain actually drives through in different ways depending on whereabouts it is within the wall. But what they were able to show in experiments is how wind-driven rain will penetrate through quite large depths of masonry walls in experimental things. So backing up, if you like, the Derry-Connolly tests, but also the experience of that. Looking at how do you deal with that, one of the most effective ways, and you can do it, is you render your wall. So you plaster your wall, and that solves the problem. Unfortunately, we've got very large numbers of very nice stone and brick buildings where it's not really aesthetically acceptable to render them. But if you render your wall, and that's why traditionally in a lot of West Coast areas, the walls have been rendered. And render is a very, very effective way of getting out. And it can be full renders, or even this is a building we did in Old Castle, which we rendered. It's a Harling, a very light lime-based render, but it stopped the water getting through as well. And you can still read the stone patterns behind it, but it was very effective at stopping water. We also did a full-scale experiment at grouting walls, in other words, filling all the voids within the wall. So what you're doing here is acknowledging that the rain is getting through your first bit of stone, and then it's finding its way through the porous center part of the wall, and then into the inside. So the English Heritage experiment was you grout this wall. This is incredibly expensive to do. If you imagine within a wall, 2 foot thick stone wall, and you're trying to find every little void within that and fill it full of a mortar, a lime mortar, incredibly expensive, and also really difficult to know whether you've actually got all the voids or not. And so I think their outcome of this was that it's not really, in most cases, it's not really a practical day by day solution because it's so expensive, nobody can afford to do it, and it doesn't even guarantee to give you the results either. But it was an interesting experiment. They were working down in in Devon, and you probably noticed the stones of those. There's particular difficulties with impervious stones, and we have the same difficulties with basalts on the left, granites, and very hard limestones. There is no porosity in these stones whatsoever, so you don't get that sort of stone getting wet and drying out at all. Everything is happening in the joints and in the core of the wall. And a sure sign that you've got a problem in your building and water in the core is when you start to see any of these things happening: moss growth in the joints, plant growth in the joints, calcites leaching out and stalactites forming on the outside of that. If you see that, you'll probably, if it's been happening for a while, the core of your wall is probably washed out. You've probably got big voids because a lot of material has been washed out. There's been water getting into the core, coming out, trying to get out through the joints, quite often going inside as well. But you've got a porous core within the wall with a lot of water getting in and down through it. Quite often what people do to that is they slap a load of sand cement render on the inside, and then they put a bit of beauty board over it to hide it for a while. And that works for a while. This is a church we repaired. Top left is the beauty board. We stripped that off, and there was mouldy, dry rot-ridden cement render on the inside. So we stripped all that off as well, and effectively just lime washed the inside of the wall, tied in with repointing on the outside. But that doesn't actually stop all the damp getting through. So the question is, and we quite often ask our clients, is there an acceptable level of damp that you're prepared to put up with? And you deal with it by ventilation or a little bit of heat, keeping air movement through the building. In this case, it was a bell ringer's loft, so they didn't mind. They were only up there once a week, so they didn't mind too much that it got a bit damp. But to try and stop that completely getting through would have been enormously expensive for them. But all of this, I suppose, is leading up to this thing of, well, how do we understand what is happening to this water within the walls? So we now know that there's water penetrating through the walls. We now know it's moving through the core. It quite often comes out somewhere completely different from where it's gone in because it's moving through the core and finding it. How do we start to understand that to know how to treat it? And that's a lot of what current research is doing, and the person who's doing that research is here in the audience tonight, Scott. And what this is about is the next stage of trying to understand how we can assess how water is moving through walls, and then once you start to understand how it's moving through walls, well, then you can start to realize what you do to treat that and to understand that. So what Scott's been looking at is ways of measuring the moisture in the depth of the wall, non-destructive ways. In other words, not drilling big holes and sticking in traditional moisture meters into that, because quite often these buildings we can't drill big holes in them and take that. But non-destructive ways of measuring the moisture content in walls, and therefore being able to build up a pattern of that within the wall. So what this is about is finding it's a big, long, ambitious challenge there for Scott, but a non-destructive, reliable, practical, quick and economic technique for measuring water content. So the sort of holy grail of this is, if you like, it's something that a contractor can use on site or a surveyor can use on site, and we can track the movement of the water through it, and by finding the pattern of water movement, find the source maybe of the water getting through, and find how it's getting through the depth of the wall, but also moving down through the wall as well. And this is Scott working away last year on New College in Edinburgh. One of the what we tend to do is use our buildings as guinea pigs for these experiments and stuff. In this case, University of Edinburgh building, very willing to help, very keen to help. We were on site repairing, repointing, cleaning the building. So the scaffold was up. So that gave a test bed for Scott to come along and experiment, in this case with a microwave measuring device on that, and then with ground penetrating radar. Scott, am I right, Amda? Yes, good. GPR techniques on this. And what Scott is trying to do is look at calibration of those to see if you can compare different techniques and try to understand how we can get a practical way to measure moisture content, not on the surface, but in the depth of the wall. Well, the surface as well, but on the depth. So Scott was spraying this wall with water to simulate wind-driven rain. It was inside a protected scaffold, so it was if you like, the normal environmental fluctuations were taken out of it. Scott was spraying it with water, and then in time after that, seeing what was happening to the moisture at depth within the wall. And this is, I mean, it's still early days and it's still experimental, and there's lots more can be done on this, but it's producing really interesting results about that. And one of those results has been a realization that the standard tables we use for wind-driven rain in this country are probably not accurate anymore in terms of the actual wind-driven rain that's hitting buildings. And Scott is just in the final stages of writing 2 papers on that at the moment, which is explaining why we don't think, or why he doesn't think they're accurate anymore, but starting to look at ways in which we can get more accurate tables to show the amount of wind-driven rain that's hitting buildings, and that's a sort of it wasn't where we set out to go, but it's something that's come out of this research as well. And out of all of that, I suppose, is this thing about why you know, where are we trying to get to in this? And really, what we're saying that moisture movement is probably the single most damaging thing to our historic fabric, moisture getting into buildings. We know, we've seen already, there's greater intensity of water, so climate change is happening in terms of that. If you don't get it right, it's pretty catastrophic in terms of the fabric of the buildings. But we're still a bit off in terms of trying to find really good practical ways of measuring, charting, recording that. Unless any of you know of somebody who's also busy working away and has discovered the new magic tool for doing this. But there's a lot more work still to be done, lots more potential for research. But it is going to become increasingly important, I think, in terms of preventing damage and solving damage to historic fabric. I'm probably nearly up my time, but I'm going to keep going if you don't mind, wherever Stacey is, because I wanted to show you, I suppose, a bit about why we're doing this and what we do with that information once we get it. And I'll run through these a bit quicker in that. And so, you know, what we're doing about is repairing and conserving historic fabric, and we do that, you know, we have to do it in a very, very detailed manner. So we start off with trying to get proper surveys of buildings now. And one of the great revolutions of the last 20 years, and I've been working, is the ability to get, at relatively cheap prices, stone accurate, highly accurate, detailed drawings of buildings using LiDAR surveys. And so we can get our building and we can start to produce drawings like this fairly easily. You can use the scan data. This is just a point cloud from scan to build up patterns, I say, relatively easily and cheaply now. You can go from your building, your scan data, your point cloud, and then start to produce accurate drawings, again, you know, relatively cheaply. And those are obviously and highly accurate, highly accessible. Handheld scanners can do this now for detail. Stonemasons are using handheld scanners on site for taking details of a stones to reproduce it. They can take the scan data, they can put it back into their CNC cutting saws in their works, and they can produce highly accurate replacement stones. So this is, I suppose, from the scan to the drawing to the cutting shed and producing the replica stones. And it can be done really accurately. Now, obviously, stonemasons have always been able to do it really accurately, but the important thing about this is that it actually makes it economic to do really accurately. So the cost of doing very good quality stone is, relatively speaking, coming down. And it's a combination of the scan information, the availability of materials, as quarries open up, CNC, computer-controlled cutting saws, you can take a lot of this sort of donkey work out of it, and that leaves the artist, sculptor for doing the fine detail and the carving later. Other survey techniques, this is a GPR, again, on an Irish stone cross. What we were trying to work out here was the buried metal within the cross, holding it together, and whether that buried metal was starting to rust and that. But GPR and also, again, the scan data can produce this very highly weathered stone, obviously, but producing accurate records of that. Again, relatively cheap now. But there's still no, in our view anyway, there's still no a sort of alternative, but to get up close to the building that you're going to be working on. And we do that if first choice is using cherry pickers and scaffolding is available. Quite often we upsell in to look at buildings when we're in the early stages of it, because if you're not looking up close at it, you miss things and you can't see things that are wrong, and you get it wrong in terms of that. And the typical things we're looking for, like on the right, the buried metal within the buildings, rusting, blowing stones apart, blowing brickwork apart. It's very hard to see that from either scan data or from standing on the street or even with binoculars until you're right up close. Quite often you don't see what's going on. You get up close, you can find, as we often find, that there's bits about to fall off. And we quite often end up when we're surveying, we end up taking them off. But getting up close to a building is crucial on that. And that's sort of leads into the work that we do in trying to repair and restore these buildings, and say moving from the drawings right through, and so that previous slide. So that's the building. Top left is the stone detail we prepared from the scan data, and that's the process, if you like, of going from the scan data, the original replacement stone, and the replacement stone being put back in to the walls. And because of the advances of technology, that's now relatively economic to do, and because it's relatively economic to do, clients are more prepared to get it done and to repair buildings properly. So you get buildings being looked after, I think, more than before. It's fairly crucial in this that we try and create the right environment for doing the work. So most of our big projects now, we would go for a covered scaffold, or even ideally a complete roof over the building, because you're allowing the building to dry out. You're working in a controlled environment. When you're repairing a roof, you're not letting water into the building, particularly if there's an important historic interior underneath it. Again, the sort of technology of this has been more cost effective now than it used to be in terms of these large span roofs that you can put over, and nearly always they're worth it because you can work through bad weather and you can get the right environment for doing the work within. And this combination of, say, of the technology, the availability of the stone, means that there's a resurgence, really, I would say, in the stone industry here in terms of the quality that can be done, and therefore the scope of it, and that creates a virtuous circle because more people are looking for it, more masons can come in and go back into it. And it's also, I think, led to a resurgence in stone in new buildings as well, not just as cladding, but in terms of losing. I'm out of time, but I'm going to very briefly run through these because we've been involved as well in, we don't design new buildings generally, but we've been involved in selecting the rock for new buildings, and this was a UNESCO World Heritage Site, Giant's Causeway Visitor Centre, local quarry, used very contemporary design, Hennig and Peng architects. But if you don't understand what you're doing, it can go wrong. And this was also a new building where the stonemasons, the architect and the contractor didn't quite understand what they were doing, and the whole of that facade is going to have to be taken off and replaced. So if you don't understand what you're doing, it's very easy to get it wrong in terms of stone selection, how it's put in that. I've run out of time, so I'm going to run through these very briefly. I want to show you again what we're involved with is trying to get quarries opened up again. So these are traditional quarries. Stone industry sort of fallen into decline, but we're in two cases now we've been able to get involved in reopening quarries to produce, and these are both in Ireland, really, really good quality limestone, which has been now used on an extension to an historic hotel in Limerick, and this is all new. This is brand new limestone in a reopened quarry, and it's not cladding, it's solid stone masonry built by J.P. McManus, one of the richest men in Ireland. But it's brilliant because this is reviving the industry, things like this going on. And this is all, let's say, new built stonework, London-based architect. We were working on the stone selection side and finding the stone, opening the quarry. But it is a fantastic example of the capacity of the industry, again, reborn, and it's partly because of the value of it. So finally, why bother? Last few slides, Joseph, and that. Why bother? Because we have this fantastic built heritage that needs looked after, really. And buildings all buildings get a bit sad and go into decline and get things happen to them over the years, like this glass box being shoved on the side and disregarded and left to sort of moulder away. And locked inside them is a sort of fantastic heritage, and it needs looked after, it needs repaired, it needs to be restored and valued again. And this one, mixture of brick and stone, but a sort of understanding of all of that in terms of restoring the fabric, but also then in this case restoring the historic interior of it as well and bringing it back to life as well. And this is one of the buildings in Queen's University. And it's that bringing back buildings into life, which is the heart, I suppose, of what makes all the work that we do interesting. But at the heart of that, I suppose, is understanding the fabric, the historic fabric, and understanding what you can do to restore these buildings, put them back into use, and I say, make sure that you're sort of passing them on for another generation. Thank you very much. And I've spoken for too long. I know I'm 15 minutes over my time. Sorry.
I personally didn't have enough. I think a fabulous account of problems and some solutions. I learned a lot, and I'm sure there are going to be many questions. Please, when you ask questions, I would be grateful if you could introduce yourself and also mention your institution, if applicable. Any questions for Dustin? Yes,
Hello, sir. I'm Shohini. I'm a student in this institute. And in one of the slides, you showed us an example where you used the lime putty render on the exterior wall.
Yeah.
Stone wall. Was that the original feature? Was that done afterwards?
So that building was a 16th century tower house, which had been rendered over with a cement render. But when we took the cement render off, we found traces of an old lime harling underneath. So we think it had been lime harled traditionally. And the stonework was not, if you like, posh stonework, it was rubble stonework. So it was actually the Scottish Lime Centre, which some of you will be familiar with, came over, analysed that for us, and then in fact they sent over a couple of their people to train up local, because it's lime harling, it's sort of gone out of use pretty much completely in Ireland. So the Scottish Lime Centre trained up some of the local plasters, and then they replastered that with a breathable lime harling. So we were pretty sure it had been harled originally or lime rooted, but it had all been stripped off, and say, well, when we found it, it was a very hard cement render on it. But that had all cracked and water was getting in and penetrating its way through. Yeah. So lime harling is a very effective coating, but obviously for aesthetic reasons you can't use it everywhere, at all, but it's very effective at keeping water out.
Matthias Sturridge, Deputy Director, UCL Institute for Sustainable Heritage. Thank you very much for this really phenomenal presentation. Without wanting to point a finger at Scott.
Please do, yeah.
Whether you could tell us a little bit about your experience as an industry supervisor on his project. You're the industry supervisor on his project, aren't you?
Yeah.
I wonder if you could tell us a little bit about your experience, what it's brought to you as CONSAR, and whether the research has had any impact on how you do your business.
Yes, I'm happy to do that. I'll probably say it's not the first time we've acted as an industry partner, and in every case we've learned a lot from it, and we are learning a lot from Scott's project. The value we see is because we are wrapped up in the day-to-day of practice. So you have the clients shouting at you. You've got timescales and programs to work on. You have to have the building completed within a certain amount of time, and it's all too easy. You sort of rush down a solution very early, and the way the industry has gone is that design time and thinking time has been compressed. In fact, the whole program of building has been compressed, but the design type in particular has been compressed, and you're expected to come up with the solutions very early on in the process. And that's a struggle when you're dealing with any building, but when you're dealing with trying to work out, what's happened or what's happening to the building. So where we see the value in the industry and the research partners is getting us the information to be able to feed into that very compressed timescales on a job. We don't have the luxury of doing the research on the jobs we're working on, but if we can do the research in parallel to that, at least we can feed the learning experiences back into that decision-making process within that. So we're working on, why we were interested in getting Scott up to Edinburgh is we're working on 3 or 4 buildings for the university at the moment. One of them in particular, the old Royal Infirmary, has been suffering from a huge amount of dry rot over the years. We're only uncovering the depths of that as we strip back the many layers of health service partitions and suspended ceilings. But water has been getting in through the masonry as well as through the roof and stuff. And we were trying to understand how are we going to stop that water getting in the future and how it's working. Because the last thing the university wanted was, having spent many millions on their building, to find that it's leaking at the end of our project. So even the work that Scott has been doing, even on the side issue, if you like, of weather patterns and how rain is falling on a building and how you assess that and measure that, all of that we try and feed back into the project. So we find working on, not just with Scott, but with as an industry partner, we find that enormously valuable, I have to say.
Fantastic, thank you. So can we quote you that Scott's work has saved an investment of several million?
I'm sure we could say that potentially as saving a, yeah.
You mentioned a little bit about rising dam, but wondered if you could say a little bit more.
Okay, right. Yeah, so rising damp, obviously it's the salts in the rising damp that tend to do the damage. So when you've got high pressure in groundwater and the water's rising up through the stone and then coming out through the stone, that tends to very damage. You'll see the tide mark on buildings as water comes up and through, and that's the salt movement through the stone is what's breaking down the surface of the stone as it comes out. And there's quite a lot of research on this. I mean, I think that Bernie, I know, did a lot of research on it. So there's quite a lot of sort of research on that movement through it. Where we've been involved, I suppose, is what do you do to try and stop that? And so you always start from a point of view where you're trying to reduce the pressure of the groundwater. So the first choices are getting in drainage at the foot of the walls on the outside, trying to remove the water pressure from going up the walls in the first place. A lot of the buildings we're working on, you can't easily install a physical damp-proof course in them. So a lot of the emphasis is on external drainage and reducing the groundwater pressure on that. But quite often, low plinth wall, we would leave the joints open on the stone. So there's not much. So if you think about the plinth of the wall, if the joints are open, there's not much damage you're going to do by rain getting in through there because it's going to go into the ground. But if the groundwater can come up and go out through the joints, then it doesn't go up the wall. So trying to encourage the water to come out through the face of the wall is the first choice in that. Quite often you see people plastering and putting tanking on the inside. All that tends to do is push the water higher up the wall. It's trying to get, and sometimes you have to do that because of precious interiors and things, but trying to let the water get out at the foot. So leaving the joints open, especially the perpen joints, the vertical joints open. If you do have to repoint them, it's the weakest of weak mortar, so the softest of soft mortar, so encouraging water to come out through those joints as well. But drainage is one of the things. We have used, and we do tend to use electroosmotic damp-proof courses, I have to say. Now nobody can tell us the science, well, the pseudoscience behind it. But we have actually found them effective, but we've always used them in combination with drainage and the joints being open. So I couldn't actually say whether it's the electroosmotic damp-proof course on its own is working, or whether it's just because it's a combination of things. But it has the advantage of it's not a physically too intrusive in terms of using it, because it's a series of holes in the walls and copper wire put into them, a small electrical charge. But a lot of people will say there's a lot of papers written saying it couldn't possibly be doing anything, but there are still manufacturers who will put it in and give you a guarantee. But usually when they do other things as well.
We have time for a couple more questions. There was one there, then one there, then yeah.
Hi, Valentina Valentoni from UCL Institute of Environmental Design and Engineering and UK Centre for Masonry Buildings.
Okay, all right. Oh dear, right.
Very interesting. And I have a question on dry rot, wood rot.
Okay.
Do you use any preventative measures? How do you treat it?
Well, I mean, the ideal thing to do is to get rid of the moisture, really. That's what we try and do. What's incredible, I mean, wet buildings take a hugely long time to dry out. I mean, the buildings we're dealing with, which got 2 foot thick stone walls, if they've been wet for any length of time, they could take 3, 4, 5 years for that to dry out completely. So the difficulty is being, even if you stop the water getting in, you've still got a lot of moisture within your building. And the building process tends to add more moisture to a building, plastering inside, screeds going in. So it's easy to say, get rid of the water, but it's really, really difficult to do that in practice. So in theory, good conservation practice will say, get rid of the water and you don't need to worry about dry rot because it won't happen. In reality, there's not too many clients will be happy with that on their own, and they'll be looking for guarantees from people. And none of the companies will give you a guarantee unless they've gone in and treated everything, drilled every timber, injected chemicals into the ends of it, repaired it, isolated those timbers from the wet walls, and so on. So in practice, we end up working with dry rot treatment companies because they're the ones who give the client a guarantee. Now, the guarantees are nearly always, if it's dry rot break again, that they'll come back and retreat it and nothing more. So they're not guarantees that it's not necessarily going to happen. So it's a really tricky one. Moisture, if you've got the luxury of time, what we do is, in some cases we have done this, in very important buildings we've done this, we've re-roofed it, got the water, stopped the water getting in, and then left the building for a year or more to let it dry out before the internal refurbishment starts. And in a few special cases, very important buildings, you can do that. You've got the time to do that. But putting in new materials into a building which has only just been stopped is, you'll get dry rot breaking out again because it'll still be very wet. So it's a long answer, but it's a difficult one to sort out.
Solutions within reach. There are certain parallels and great similarities with existing buildings between stone and masonry buildings or traditional construction. And I'm just conscious that there's an awful lot of effort being put in by governments to improve thermal performance in buildings. What you're effectively highlighting is that the walls are in fact non-ideal most of the time. They're substandard, they're grotty. What's your opinion of people or of thermal models being used to fix performance in practice? Yeah,
well, it's a good one. I mean, thermal imaging, again, can be used to pick up moisture within walls. It's not as sophisticated as what Scott is looking at in terms of the exactness of it, but it can be a useful first go in terms of that. I mean, it's a whole other and really complex subject when you start then adding insulation to the inside face of these walls in terms of how you're affecting the sort of thermal, the sort of where I mean, the big risk is if you get a dew point within your wall or between your insulation and your wall and you get condensation building up. So it's a very complex thing to decide on how you're going to upgrade these traditional walls to get your insulation, but without causing more problems within that. And I probably don't have time to talk too much about that, but it is really difficult. We find it constantly changing in terms of what the manufacturers of the insulation materials are saying, what experiment is showing. We try and look at breathable. Well, we either try and do it either with a ventilated layer between the insulation and the wall, so as you're getting ventilation up the back of it. That does take a little bit away from the effectiveness of your insulation, but it does at least sort of remove the risk of condensation. We're looking at the moment, I was saying earlier on, we're looking at a cork lime-based render at the moment for this building in Edinburgh. We're looking at directly plastered onto the wall, no air gap. In other words, a breathable insulation on the inside. It doesn't seem to have been used on a large scale in this country yet, so we're slightly nervous about it. But the theory being that the whole wall is acting as one thing then, as opposed to two separate things. But it's when you start to try and get your thermal performance up, that's a whole raft of further considerations, definitely. Yeah.
I'm the director of the UCL Institute for Sustainable Heritage. Thank you, that was very interesting. A lot of your images showed very decorative rainwater goods.
Yes.
And also that some of them may have been replaced in order to have rainwater goods with greater capacity.
Yeah.
Is there a halfway house in this? To what extent can they be adapted? And are we sacrificing a substantial amount of the significance of the building in actually ripping them out?
Yeah. Good point. In some cases, well, I suppose in some cases we find that the originals are rusted and rotten away, and we're having to replace them anyway. But you're right, in some cases we have to leave them there, and we know they're undersized. So what we're doing then is building in elaborate overflows and ways to get so if you get a storm blast of rain, we're not expecting that to be dealt with. It shoots out an overflow clear of the building. And that's another way of accepting that your capacity is not enough, but you're finding a way out of it. Because if you don't do that, it'll overflow, dribble down the building, or it'll go back into the building. So building in overflows is one of the ways to deal with storm surges and keep your historic fabric. Yeah.
Time for one last question.
Stephen Lebrant, Heritage Architecture. I think the climate change issue coupled with energy conservation issues is a massive problem that is for historic buildings, which we're heading headlong into without really knowing what we're coming into. You've just shown us some examples of how you might start dealing with that, using things like insertions and remaking damaged, eroded stone and things like that. Do you think the SPAB needs to rewrite its manifesto?
Ooh. How long have you got on that? Well, I think I suppose we do try and follow all the principles within the charters and conservation, but we tend to take each building as its individual and what is right for that building. Quite often you're influenced by the client and you're influenced by aesthetics as well. But I think we have to go beyond just keeping things as they are, because the climate is changing, and we have to try and make the buildings capable of dealing with that climate change for the next 100 years of its life, and that often means adapting them and making them fit for purpose in that regard. So quite often we're doing more interventions than SPAB would traditionally have seen, but we're doing it with the intention of making the building robust for the change that's happening. So that it's sort of it's justifiable by that extent. But you're right, it would a lot of what we do would not fit the SPAB manifesto in that. But it's done. I'd say we don't do it. Everything for every building is different, and we're doing it to try and conserve the integrity of that building for, for the future, really. And people talk about climate change as about as something that's going to happen. It is, in our experience, it's happening already. We're getting these intensities of rainfall, higher winds, and the buildings are not coping as a result of that.
We are out of time for questions. I sense there are many questions that can continue afterwards over a drink. I think it's time to give our speaker a break, thank him, and we'll meet upstairs at the first floor for a small reception. Thank you.
Thank you. Yep.